So welcome everybody to this session of the Chilean Probability Seminar. We have the pleasure to have with us Diederik van Engelenburg, from the University of Vienna, and he will discuss about the duality between height functions and spin models. So you have 55 minutes. I don't know.
Okay. Let's see. I planned on something like this, but maybe I don't know. I tend to be a bit quick, but maybe because it's very late, I'll be very slow at some point. I don't know. Yeah. So thanks. Thanks a lot for inviting me. So this talk is going to be mostly based on joint work with Martin and Liz. Yeah, so about duality between spin function and the integer valued height functions, and yeah, so I plan to really give a long sort of part of the talk about just some general context and sort of the type of questions that we're trying to understand. And then I want to say something about Fourier duality that we're using, which is also quite general, and I'm hoping to sort of at least give a message of the techniques that we're using. But I will simplify things quite a bit so that we actually get to results. Otherwise, it's like very technical and it takes a lot of time to get to the results. And the main thing I want to sort of talk about is a BKT transition, which I will explain exactly what it is about. Because our latest paper, I mean, we have two papers on the BKT transition, and another name for our last paper could be an even shorter proof for BKT transition, because now it's maybe okay together with if you input like one result, it's very, very short, maybe like 1 page or something. So yeah, let's get started with sort of the general context that we're having. So overall, through the talk, I will denote graphs by gamma because G, it will be a group most of the time. So and we take them to be most of the time finite, but sometimes you will take an infinite graph, like think of the lattice Z2 or something like this with nearest neighbor connection. We fix a locally compact abelian group, which will be the place where the spins will take value. Then we take a state space, which is just a map, all the collection of all maps from the vertices to G, or you write it's G to the power of V or something like this. There is a temperature parameter, which is sort of the only thing that's going to vary. We fix everything, and then the temperature is going to be the thing that's varying. And to confuse things, we often take the inverse temperature, so that's beta. Then we take a potential function, which is something that's going to measure the energy cost. So let's say that I think to give examples would be good. So that's coming in a second. But this will measure the cost of some neighboring configuration. So the energy will always be something on two neighbors. And then there is a Gibbs measure, which is which gives to every configuration it assigns a weight, and the weight will always be proportional to e to the minus beta. The sum over the edges, and then here you can think of it as the difference between two neighboring spins on an edge. But let's really see the examples coming soon. So what it means is that you are trying to favor things which have low energy cost, right? So the higher the energy cost is going to be, the less likely you are to be picked. And then everything is with respect to the Haar measure on G to the V. Okay, so it doesn't really matter what normalization you pick for the Haar measure, because you normalize everything anyhow. So that's a probability measure. So just to give this type of context, really in most generality, that's why we're here. But let's immediately dive into some examples. So maybe the most famous example is the Ising model, in which case the group will be z2, so or z over 2z, also identified with, you know, just putting +1 and -1 everywhere, minus 1. So this would be for, let me just draw a small example. You know, here I have a lattice drawn for you, and on every vertex you just pick, you know, you pick a spin. It's, in this case, it's either +1 or -1. And that's going to be your whole configuration. So every vertex, to every vertex, there is a spin associated to it, and it's a plus or a minus. And then the weight for the Ising model, well, you're just going to say the weight is going to be 0 if you have two things that are neighboring each other that are the same. And the weight is going to be 1 when they are different. Okay, so that's the potential function. So, or -1. It's -1 when they're different. So that's, you know, it favors things with energy 0. The energy cost is going to be -1. Okay, so, and then, you know, the whole weight is going to be just e to the minus the number of discrepancies or something. Right, so that's the whole weight, maybe beta as well. Okay, so that's the Ising model, but maybe something which is closer to what we're going to study throughout this talk will be the group that we're taking is S, so it spins on the unit sphere, so e to the I theta, where theta is in 0 and 2 pi. And to every vertex, you know, I have an angle sitting there. So maybe, I don't know, do I want to draw all the angles? Maybe not. So at just every vertex, you have an angle sitting there. And here the weight will be, you know, proportional. For every edge, you're going to compute something which says, you know, what is the difference between this angle and that angle. Okay, and the weight is going to be proportional to e to the minus, you know, the computation that you pick, your favorite weight that you pick on there, basically. By the way, what I didn't say, but what's definitely true, is that at any point, if you have a question, please feel free to interrupt, or if you want to write it in the chat, then maybe a video can just interrupt and say it, because I might miss the chat. So these are two examples, and maybe a final example that's still going to be very important for us is, you know, where I picked the group Z, and maybe this is less, you know, thinking of it as a spin, but it's still a group that you can take, and then every vertex, it will just have, you know, some number associated to it, taking, you know, some integer value. And this such a configuration, I don't know, typically people will call a height function, right? Because you can sort of think of it as something living on top of your lattice where it has different heights. And yeah, okay, you pick a weight that just looks at the difference between the two heights. So it will be some function, or yeah, let me run it u here. It will be some function that depends just on the difference, right? So -3, you know, and here it will be 5 - 7, so 2, you know, that's what it's going to depend on. That's the type of things that we're going to look at. Okay, so just to put them in a list, the Ising model is the group Z2 with the potential, yeah, okay, written in a bit of an annoying way, but that's because, yeah. And the POTS model is not so going to be very important for today, but it's kind of like an Ising model, but then you have like Q states instead of just 2 states, so maybe you have 3 type of spins. The XY model is going to be very important. There, the measure you're going to take on between the edges is just going to be the argument between the two neighbors. And another nice example to keep in mind is where the group is still continuous, but now you have R, and your potential function is just going to be, you know, here you must think of, you take the gradient of a height function, right? So you take 2 neighbors and you're going to compute it for the difference between the 2 neighbors. And that will be a GFF, so a Gaussian free field. Okay, these are kind of like nice models maybe to keep in mind for most of the talk. And the general kind of question that we're trying to understand, maybe the first thing is the existence of a phase transition. So what happens when the temperature varies. Okay, so that's the first type of question maybe that you want to understand about these models is if you have picked your model, you have picked your group, your potential function, your graph, everything, and you want to understand what happens when you vary the temperature to this type of model. And a phase transition, for example, for the easing model, so when your group is Z2, would be something like, okay, I'm looking at a very big box, a graph, my graph will just be Z squared with nearest neighbor interaction. And I'm going to look at a very, very big box, and I'm going to impose that all the spins outside that they are plus. Okay, everything outside here is plus. And what I want to understand is I take a very big box, and the radius of the box is going to be n, and I want to understand, what happens to the spin in the center. Do I still see the boundary condition? Do I still see that I have put plus everywhere on the boundary? So let me write it, using this notation of Gibbs measures. Okay, lambda n is just a choice, plus for the fact that we have plus boundary condition. And I'm kind of interested in what happens as n tends to infinity. Okay, just assuming here that it has a limit, but let's not worry too much about that. Okay, and it depends on the temperature that we're putting in. And we're basically asking what happens in a limit as n tends to infinity. And you're basically, so what we want to understand is this limit, in a limit, is it going to be 0? So in which case, it doesn't see the boundary at all, because the expectation is 0 also when I would put no boundary conditions. Or is it going to be large? Is this limit going to be equal to 0, or is it going to be larger than 0? Right. So that's the first question that we're trying to understand. And for this model, there is a really nice argument. So let me draw this thing again. And it's very good to have this argument in mind also for the rest. So I have all these plus boundary conditions. And what has to happen, if for my spin at the origin to not be plus? Well, there must be some sort of circuit around it where there is going to be minus inside everywhere. It could be much smaller than this particular circuit, but this is something that has to happen. And in some sense, you can find sort of the first circuit that you must find in this way. And it means that you have plus everywhere outside and minus everywhere inside. Right? Some configuration like this you must find. Another point is that if you are in the setting of the easing model, for something like this to happen, well, the only way that two spins that are neighboring each other can be different is when everything outside is plus and everything inside is minus. But each such discrepancy has a cost of e to the minus beta, right? Just by themselves. So it's going to be a product of these costs over such a whole circuit. So the idea is that, just heuristically, take beta very large. So the temperature is going to be extremely low. Then you can make the cost of finding such a circuit extremely high, right? So the probability of finding such a circuit will be extremely low. And you say something like, well, the probability that you find such a circuit tends to, okay, not finding exactly such a circuit, but okay, finding this circuit is very small. So this implies, well, at least heuristically, that this limit, as n tends to infinity, of the spin at the origin should converge to something which is larger than 0. Okay, this is just very, 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 very heuristically. And this is known as Peierls argument. Okay, you can make this rigorous. And it works not just for the easing model, but it really works for all models where you have a discrete spin space. Or not discrete, but if your spin space is finite. So let's say the Potts model or the easing model or the clock model or whatever, this argument works. So given that we have such a transition, I just want to say that you define the critical temperature sort of as the point where the transition happens from, you can also show that when beta is small, there you don't have that this thing is going to be 0. So this limit is 0. Well, this is the limit. So this is the limit of the spin at the origin. Okay. So this is defined as this mu gamma. Okay. So you define the critical temperature as sort of the first time that you see it, and that's what we will call like critical temperature. So maybe the next question that at least in physics that people try to understand is, you know, what happens at the critical point. It's not clear at all what happens at the critical point. It's not clear if there is going to be, you know, infinite clusters of plus things. What is the geometry of the cluster? What happens near criticality? Can you have something like scaling limits? Everything, all these questions, you know, these are kind of questions that people are interested in. But the first basic question is just, you know, is there going to be a phase transition at all? I think this is sort of the first question that you have to tackle in statistical mechanics. And for the Ising model, a lot of these questions, you know, you can actually do something. You can actually prove it, a lot of things. And I think for the Ising model, there's a lot of interesting stuff done. But for today, we're trying to focus on something slightly different. It's where the groups are continuous. And the first sort of example that I like to just keep in mind is, well, you know, what if I take a Gaussian free field? So a Gaussian free field, you know, my group is R. My potential was, so my weight is something like e to the minus sum over the edges, the gradient of h along the edge, e squared, and then a beta. Okay. But because the Gaussian free field is a continuous field, and because of the way the potential is written, if I rescale my field just by the square root of alpha, so alpha is some positive number, then you have, again, a Gaussian free field, but you have only scaled the parameter of time, or the parameter of temperature, right? So, well, that kind of implies, at least, yeah, this implies that there cannot really be a phase transition, you know, in the behavior as the temperature changes. Because, yeah, I mean, at every temperature, it kind of looks the same. Only, you know, the parameters change, but nothing of the actual behavior will change between. There will not be a point where it really drastically behaves different for different temperatures. So for this particular continuous model, there is no phase transition. So the next question is, you know, is this always true for groups that have a continuous symmetry? And there is another question, which is, well, what in the case where the group is, you know, well, it's not finite, but it's still discrete. And it turns out that these two situations, they are very much linked to each other, okay? So this is really what we're trying to focus on these two, the setting of either the group being the spin space S or the group being Z. And because the techniques that we're introducing only allow for abelian groups, I'm just skipping all the other ON models for today. So no non-abelian things where it can even be more weird and it's even less is understood, I would say. Okay, so let's take an example, and the main example to keep in mind for today, which is the XY model. So here my group is the unit sphere in 2 dimensions, which I identify just with the angles, you know. I just take an angle in 0 to pi everywhere. And my potential will be the cosine of the angle difference between 2 neighbors. And then, so let's go to the first question. Is there a phase transition in this model? Okay, so that's really the basic question to ask. And the answer, at least in the way that I first said what a phase transition is no. There is no phase transition, and this is something proved by Merman and Wagner in the 60s, I think, sometime. And they have an argument that really shows that if you have a group with a continuous symmetry, there will never be order in 2 dimensions. And the argument is very, very similar to the Ising model argument. That's why I want to show it. But it really uses the continuous symmetry. So now I take a very large box. So this box has size roughly, you know, radius roughly n. I put on the boundary, I I point my arrows in one direction, so I take one angle everywhere on the boundary, and I'm asking how much energy does it cost to rotate the arrow in the center. But because I have a continuous symmetry, you can slowly rotate everywhere. And it turns out that the energy of something like this, so the energy cost, you can do the computations, and it's roughly, well, 1 over log of this distance. Okay, that's roughly the energy cost of doing this. So if you take n to infinity, that's at least the heuristic of it, then this doesn't cost any energy, right? Because you can sort of so slowly rotate it that you don't see this at all in the limit. So this argument breaks in higher dimension. So maybe the next question is what then? So maybe I should mention here that if the dimension of the lattice underlying mention actually also. If the dimension is larger than 3, then there is a phase transition in the way that I wrote it before. So this is due to Froelich and Spencer and Froelich, Simon and Spencer. But in 2 dimensions, you can also ask, well, maybe something else is going on. And this, well, when you see the simulation, this is very, very believable. But when the physicists came up with this, I think there was no such thing as this type of simulations. But okay, let's look at the simulation because I think they are really nice. So this is when you have high temperature. Okay, so here what you see is a very, very big size of the lattice in 2 dimensions, and every angle it comes with a color, right? So it's like a gradient of colors. And you really see that there is no order at all, right? It's like the spins there are completely chaotic. It's really like there is really no like if you compare the spins here and here, well, observing one will not really influence the other one, as you can see from this picture. But if you make a simulation of low temperature, the picture looks something like this. And well, okay, we know that there is not going to be order in the sense that, the spin at the center, it will still be uniform on everything. But you can clearly see that the behavior is completely different, right? I mean, behavior between this picture and this picture, it's really not the same. And here you really see already like a very nice sort of, almost fractal behavior, as you can see. So we're interested in what's the heuristics, okay, at least at a very low level heuristics of this phase transition. And the reason something like this happens, to see it, is in terms of vortices and anti-vortices. So what is a vortex? A vortex is a face of my graph. So I have a lattice, which is a 2-dimensional thing, where if you look at the spins around it, it makes a turn of more than 2 pi. Okay, if you add all these angles up, it makes a turn of more than 2 pi. And if you look at this one, that's what we call an anti-vortex. So well, okay, if you take the same orientation and you count them around it, it will be a turn of less than 2 pi, or less than minus 2 pi, or whatever. It will make the turn the other way around. Right, so that's kind of the idea, that these 2 things, they are kind of like discrepancies, and they cost a lot of energy. To have a vortex costs energy. Okay, and it turns out that if you are in the low temperature picture, now you can actually see them here, because here maybe you can see them that I draw them. Here you have a pair of a vortex and an anti-vortex very clearly sitting in the picture, and you can actually see them all over the place, right? They appear sort of everywhere. And if the temperature is very high, then essentially what physicists call there comes sort of a plasma of these things, and they break all the symmetry that's in the system, and you get something completely chaotic. But if you're in the low temperature phase, they should be sitting maybe at They should still be visible, but they should play as a more negligible role. And if we would, you know, just pretend that they are not there, so no vortices or anti-vortices, then my spin system, which I will write as e to the I theta, because, you know, they're living on the sphere, so it's a way of writing them. It would really be equal to e to the IHX, which would be a GFF, a Gaussian free field. Okay, if there would be no vortices whatsoever, I mean, then it's just a computation that you can do. It's very, very sort of simple idea. But of course, there are vortices, and they play a non-negligible role. But this type of behavior does restore when the temperature is low enough. Okay, so this is a different type of behavior you see between high temperature, where it doesn't look like this at all, because there my spins are much more chaotic than e to the I HX, e to the I of a GFF. Okay, but at low temperatures, it does look like something like this. Okay, I wrote it here, here again. Right, this is the low temperature behavior that you're expecting. So I will later give an exact formulation of the type of phase transition that we're seeing, at least mathematically, because this is not exactly, I mean, well, we don't get this, of course, because we would have very precise computations of the effective temperature you would need for this, but you get, you know, you get the type of behavior in the end. So maybe this is a good moment if someone has, you know, a question about the heuristics or the model to enter in, and I will take some water. Okay, so oh, sorry. Yeah,
in the second simulation you showed.
Yes.
Okay, so there's like the little red parts between two vortices, but then there's all these sort of constant green parts. Are those sort of going around vortices or something like that?
I mean, I think the fact that they're green is a bit coincidental. I think they should be able to be any color.
Yeah, but they're sort of, I mean, you have these pairs of things which give you little parts which look the same color, and then you have these big.
I think you should see this type of clusters, like things where, you know, I mean, I could be extremely precise about what clusters you should be seeing, but this type of clusters, I guess they should be almost like a fractal-like behavior. Like, I think if you zoom out, you should see again something that looks very similar, but it could be of a different color, I guess. The exact color doesn't really matter. But it should look roughly the same at every scale, this picture. And then these are like clusters where the angles are, you know, maybe inside 0 to, I don't know, pi over 2 or something like that. Okay, the angle here in this green region, maybe the angles, they stay between 0 and pi over 2. And in the red region here you see a red region. They would stay maybe in pi between pi and 3 over 2 pi or something like that.
Yeah, maybe my question wasn't very well formulated. So you have these pairs of vortices and anti-vortices, which give you these little pieces like the ones you drew. But then you have like a bigger structure where these pairs get connected. Is it something like that? Like, because you have these clear contours separating pieces of different colors. I don't know if that's
this I'm not so sure about. I mean, maybe it's a bit of reminiscent of this exact I mean, okay, it's a good interesting question of what a topology actually, how it actually looks like at a very small scale. I think, okay, before we understand this, it would be very tough, I think, but it would be nice. Maybe Avelio knows better actually what So I see there is something in
You're talking, we're not listening. You're muted.
I'm muted?
No, Avelio. I thought he was moving his lips, but so Avelio, you're moving your lips, but we're not hearing.
So they are asking whether, so Roberto was asking whether there is a relationship between the numbers of vortices and anti-vortices, maybe. That's what.
The relation, yes. I mean, the number, there is, in some sense, there should be as many vortices as anti-vortices, but it could be that you have rotation of more than once around one face, depending a bit on the graph structure. So, but they should be neutral in some sense. So there should be exactly as many vortices as anti-vortices. That's sort of a physical condition that you just get from doing computation. There is no other way. Yeah.
A quick question, sorry. My question was whether there's a relation between these pairs and beta, the temperature.
Yes. So here, what you see is like when the temperature is low, I mean, the exact number I think will be very hard to compute, but when the temperature is low, the distances between them should be like typically a polynomial or something like that. And when the temperature is high, so in this picture that you see here, they should be all over the place. There should be vortices and anti-vortices essentially everywhere. So yeah, they should have a very drastically different behavior, I think. Yeah.
Okay.
Okay, thanks. So maybe let's move to general to this topic of Fourier duality, which is something that's been very productive in doing statistical mechanics in general. And a general sort of program or mini program that we have in mind is, okay, to a group, we want to associate its dual group so that we can do Fourier computations. Okay, so this is called the Pontryagin dual of a group. Then for functions, we want to understand what their Fourier transforms are. So this is very well understood in our setting. Then to a model, we want to associate a dual model by doing Fourier computation on really a big system of things. And then the last step is to transfer information such as, this thing here, which is called the 2-point function, for example. We want to transfer information from one model, so our spin model, to something on the other side of the Fourier transform. And this is the big question mark overall. So this is often hard to do, this last step. But in general, this is kind of the mini program that we have in mind. So, and we will see later why it's useful to do that. So in our setting, the group that we have in mind on the sort of primal side, we'll call it the primal side, will be the sphere again. So these are my spins, taking value in S. And on the dual side, you just get the group which is a Z. Okay, this is just because the characters of the group S, they are these maps, theta map e to the I theta k for integer values k. Okay. And then, what we have is our potential function u, which is a symmetric function. That's what I will assume always. And I want to find something on the other side, which is also going to be a symmetric function. And to do that, I will always assume that e to the minus u is positive definite. And what I mean by that is if you take the Fourier transform of e to the minus u, that thing is positive, or let me just say strictly positive here. It doesn't matter so much, but so that's my assumption on u. And why is that? Well, in that case, if I take the Fourier transform, I get something, and I can just take the log of that thing. So that defines e to the minus v, right? Because I can take v just to be the log of this Fourier transform, or minus the log of the Fourier transform. But On the other hand, if I start on my dual side with the symmetric potential function, and I look at e to the minus v, so at this thing here, and I do the same computation, I look at the Fourier transform, and I look at e to the minus v, I want that thing, to be larger than 0. So this condition is very symmetric, right? I'm looking at something, e to the minus u is positive definite. Well, that's the thing I also have to assume on the dual side. Or in some sense, you can start with this assumption on either of the two sides and you automatically get it on the other side. My last assumption that I will make throughout this whole thing is that my potential function on the primal side is my u is twice continuously differentiable. And this is really more of a technical assumption, but it's important for the results. And on the dual side, this corresponds to a certain moment condition. Okay, so this is kind of the dictionary on how to go from one side to the other side in Fourier transform, but this is on the level of just one function. And we want to understand, a system or a whole model, so something living on a graph. And here is where I will make some simplifications for this talk, because I don't want to go into talking a lot about some differential forms and then losing everyone on that. So let me just stay in a setting where the graph is planar, because in that case, everything is a bit easier. So here I draw a graph, okay, any planar graph. And then I take its dual graph, which is just, to every face, I associate a single vertex. And then, well, my face is also the outer face. And I'm going to draw edges whenever two faces are neighboring each other. So here are some edges, 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 edges. Okay, and then my dual graph, which in this case looks something like that. Or am I missing an edge? Yeah, I'm missing one. My dual graph, which looks something like that. And both of these graphs are planar, so you can think of them as being mutually dual graphs. Okay, and what we're always going to assume is that the spin model lives on gamma, and my dual model height function lives on the dual graph. Okay, so by now this doesn't mean much, but it turns out that you can do, computations using these things. So on the spin side, let me define the type of thing I can compute. Okay, so this will be a spin, well, sort of twisted partition function, which I define now as the integral over s to the v, my weight, my Gibbs weight that I'm getting, e to the minus beta u. Well, I'm looking at the gradient of the spins. Okay, this is whatever you want to define it, plus epsilon e, d sigma. So this is the Haar measure on SV. And epsilon is just some map from the edges to R. Okay, this is something that I will call a twisted partition function. And the reason we call it a twisted partition function is because you can kind of think of it, well, I'm not really calculating the partition function, which would be, the thing if epsilon would be 0 everywhere. So then you take the integral of the one where epsilon is not there. That would be the partition function. But the twisted partition function is a bit like, you are preferring a slight rotation. You're not preferring anymore that the angles are as small as possible between two things. But now I'm preferring the angles to be exactly epsilon. Okay, that's my preference state. And then there are some random fluctuations from that. So that's why we call it the twisted partition function. Okay, and And that's on the spin system side. And on the height function side, I will write a measure on mu gamma star height, also with the temperature beta. That might be a bad idea. Well, here, I want to compute characteristic functions of the form let me just write it differently. Of the form where I sum over all the edges. I look at the gradient of the height function on the edge times epsilon e. And this is the type of thing I'm trying to compute. And here my v height is the height function measure that corresponds to taking the Fourier transform. So let me just write it. Theta height of h is proportional to taking the product over all the edges in my graph. Well, as we have seen, the edges in my graph are the same as the edges in my dual graph. I take e to the minus v beta dh. And my v beta here, this is this whole thing, e to the minus v beta. This is the Fourier transform of e to the minus beta times u, okay? So e to the minus v beta of this something is the Fourier transform of e to the minus beta times u. That's the type of thing that defines my height function. So this defines the height function, and I'm interested in computing the characteristic function of the height function. And it turns out that you have exact relation between these things, and I'm not going to compute it, but you can prove quite easily, at least in the planar case, it's quite easy, that this thing is exactly equal to the ratio in beta epsilon divided by z gamma spin beta at 0 with 0. So, you know, it's not quite on the right hand side, you know, I don't have quite something which is a probability measure, but it starts to look quite close to something, you know, because I have a partition function sitting below, and above I have some twisted partition function. On the left-hand side, it's just a characteristic function of something. So it's you know, in trying to understand the law of h of my height function, it makes sense to try to compute the characteristic function. And interestingly, the perspective that was used, or what people tried to compute before, was actually always sort of the reverse of this thing, where people try to compute the characteristic function of the spin system instead of the height function. Okay, and this perspective difference, for some reason, it makes a huge difference, and the reason is hidden in the type of functions that you're allowed to use, like this type of epsilon that you're allowed to use. And the next slide, you know, we get from this formula the following covariance lemma, or the covariance duality formula, which I think is a very nice sort of expression, where, you know, my nu measure is my height function measure, my mu measure is this green arrow is pointing towards, you know, the spin system measure. And the way to get this formula from, you know, this exact Fourier computation that you can do is just you differentiate twice with respect to epsilon, and because it's continuous, this is all fine. And by this, all this expression here, I mean the L2 inner product. Okay, so the sum over the edges, the gradient times epsilon. So really, how you can think of this as a covariance covariance formula, how the two covariances of the spin model on the one hand and the height function on the other hand, how these covariances are related, right? So in particular, if I take epsilon e to be just the indicator function on some edge xy, and I take omega e to be the indicator function. Okay, so this depends on epsilon. Omega e, the indicator function of ZW on some other edge ZW. Then this whole formula above, well, the right-hand side, it just completely cancels, right? Because the edges are different. And from the other two, you just get these two terms that are left over, right? It's just the gradient of one edge times the gradient of the other edge. On the height function side and on the spin system side, you get, well, the potential, okay, well, you take one time the derivative of the potential at one edge and then at the other edge. So here you can really see a relation between the covariance, or you know, the bit of the gradient of the height function between two different edges, and that of the spin system side. So here, what is maybe the main takeaway message of this whole story is that once you know that there is a phase transition in one model, in your spin model, for example, then there must also be a phase transition in your height function model, and vice versa. Okay, so they really have exactly the same behavior, at least in if you compute this type of functions. And yeah, maybe just a small remark is that this covariance formula, which I think is I think it's, you know, it's very easy to get, and I think it's very nice. But it works for all graphs. You know, you don't have to assume any further topological properties on your graphs, and not just for planar graphs, but you have to be a bit more careful in how you formulate the exact statement. Okay, but you can still use it also for other graphs. So maybe it's time to move back to the BKT transition. Okay, my father just really yawns very loudly in the room next to me. So let's go back to the BKT transition, and maybe start with the way that we formulated the type of result that we're actually getting. And this I also made a spelling error here. This type of result, it goes back, you know, at least the rigorous part of it goes back to Fröhlich and Spencer, but it was predicted by Berezynski, Kostelis, and Taulis, and yeah. So that's why it bears the name BKT actually. The statement is the following: there exists some critical temperature or inverse temperature, such that if beta is smaller than the critical temperature, then the 2-point function, so this is the, you know, this is e to the I theta x minus theta y, okay? This thing decays exponentially fast, so that is the chaotic picture that we're seeing when there were vortices and anti-vortices everywhere. But if beta is larger than some critical point, then actually they decay with a polynomial power. Okay, so there really is a completely different type of behavior, at least on the level of 2-point functions. And the proof of Fröhlich and Spencer is better because, or the actually statement is better because they have some, you know, some power here, which tends to 0 as beta tends to infinity. But that's not what the type of results that we are getting with this statement. But there were some newer proofs of roughly a year ago, a bit longer, 1.5 years ago, exactly on the same day of myself and Marcin and of Eisenman, Harrell, Paladin, Spinka, that gave a new proof of this fact. So, and for all these things, the main input is that you move to the dual model, so to the height function setting, and you try to prove something there. You try to prove that there is a phase transition. Okay, so that's step 1 of the program. And then step 2 was to move this information back to the spin model. Okay, and the fact that there is a phase transition in the height function model, that's actually something that is, or at least most of that, is actually sitting in the theorem, which goes back to Pete Lammers in 2020. who shows that, well, if beta is large enough, so if the temperature is large enough, then the height function delocalizes, which means here just that, or you can think of it like this, as I wrote it here, that if you look at the variance between 2 points that are far away from each other, that this blows up to infinity as x minus y tends to infinity. Okay, so that by itself, it would not be a phase transition, but it is known that this difference is bounded if beta is small. Okay, so this gives that there is a phase transition in the height function model, and this.
So sorry, just one question here. This is for x and y, which are neighbors as before, or this is just for?
This is just for any. This is as x and y tend to infinity. So this boundedness. Okay, this is if beta is small.
Yes. Okay. So beta is not going to infinity. So the things that are going to infinity is the distance between x and y.
Yes. The distance between x and y is going to infinity. So this is uniform in x and y. It's bounded when beta is small, and when beta is large, as you take the distance between x and y to infinity, this thing blows up. The variance. Right. So this one, it blows up as the distance between x and y goes to infinity. Okay, so that's the type of phase transition that you're seeing. And one way to think about it is maybe that, well, if you go from a primal model to a dual model, you invert the temperature. So here, beta being large really corresponds to large temperature and not low temperature, right? In a dual model, beta large is really the high temperature regime. And then what you see is that the whole model, it's really free, and the translation and variance that's sitting in the group, it's still there. Right? So this whole thing, it's invariant. This type of measures, they are invariant and they're adding something to the height function. It doesn't change it. You cannot you have the whole translation symmetry there. But if beta is small, and that means the temperature is small for this model, then actually it kind of freezes. It's very flat, the height function, if beta is small. So that's the type of picture that you see. But okay, that's kind of a side remark. All you need to know is that there is a phase transition between beta being small and beta being large. And the proof is really extremely nice, I think. So the proof is it uses like percolative arguments. There is only one small tiny thing, is that it only works on graphs that are trivalent, which means so much as that the degree of the graph must be bounded by 3. Okay, so that's a small side step. But in this type of models that we are considering, well, either you can show, okay, it doesn't matter. You can get around this problem for exactly the type of models that we are considering, but not in the generality that Pete was mentioning. Okay, so, and this generality to general graphs was, for example, in the paper by Eisenman, Harrow, Pellet, and Spinka. And in the most recent paper with Marcin, we also have a way to get rid of this trivalent graph ID. Okay, but okay, that's the only sort of small downside of this proof. Otherwise, it's extremely general. So it does, yeah, it really works for a lot of models. It's really nice. But then the remaining question is, how do you transfer this information, the fact that there is a phase transition in the height function, back to the spin system? And the two proofs that were done like a year ago, both of them, they are using a non-trivial graphical representation of these two models. And for some reason, it was, well, it was kind of bugging us that this is the way you have to do it. But yeah, we were thinking about some things. And now it turns out that if you use just directly this Fourier transform method that I was talking about, and you do the computation in the right way, you get very directly statement, an equivalence relation between something on the spin side and something on the height function side. So you get a equivalence which says that on the height function side, the height function delocalizes. So let me just recall that that means that the variance blows up as the distance tends to infinity. Okay, that's what delocalization means. And this happens only when this sum on the right-hand side tends to infinity, and this sum, it is the following thing. So on Z2, it's like you take the spin model along a line of these edges pointing upwards, where this would be E0, this E1, this E2, blah, 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 up to En. Okay, and then you continue. And you look at the gradients of, and you look at the correlation of the gradient between, you know, this first edge and the ith edge, or the jth edge. I wrote with i's and j's different. The ith edge. Okay, and that sum, in terms of these derivatives of the potential multiplied by I, if that one blows up to infinity, that happens exactly only when the height function delocalizes. Okay, so this sum is finite when the height function is localized. So when this variance thing here is finite, bounded, then this sum is also bounded. And if this sum is infinite, or if the height function delocalizes, then this sum is infinite. Okay, so then there is like one step to do is to say, well, you know, okay, this clearly shows that there is a phase transition of some form, you know, in the spin model. But the only thing you still need to do is like to transfer it back to the language that we're using of two-point function things. And that step really is something really an elementary calculation almost, once you know Genebra inequality for the XY model. So I don't want to go into that, but I want to say it's possible to get back to this language. And that is kind of the end of the story for BKT for us. So if there are questions about the BKT, then maybe this is a good moment.
So, so this one works for XY, but also works for VLAN, no? Is it, are there any other, like, because you have this duality?
Yes.
This positive.
So, yes. So I think this exact relation, so for sure the implication height function model delocalizes works for almost everything. And well, I mean, okay, so what I know for sure is as long as your potential U on the spin side, that this thing itself is a positive definite. Okay, so that's like anything like alpha I cosine I theta, something like this, where alpha is larger than 0. So any function of this type that works. It doesn't rely on any graphical representation or anything like that. So I think this equivalence, it holds at least. Let me think if there is maybe there is a caveat, but I think it works, you know, as long the equivalence it uses reflection positivity perhaps for one argument, but that's because you want to say something is positive, you know, some interaction between two things is positive. But this is really super general, like as long as your potential has a nice form, then you can do it. So
you still need to work in some kind of like a periodic boundary condition type of story, the reflection positivity.
Right. So that's the first setting to do. But since you know that for these spin models, there's no order disorder type phase transition, and you take the infinite volume limit, there is only going to be one translation invariant Gibbs measure. So it's kind of okay, but
you don't know that for VLAN. So I think that you just know that the infinite, or no, like you know that the constant boundary condition, and the free one they converge, and the periodic they converge to the same one, but you don't know that. Well, it doesn't matter.
Okay, I think yeah, so maybe you need to do a little bit of work, but I mean, the fact that you can have this equivalence, I think you can get it, because you know, if you do the computations for XY model on this graph, and then you take this villain approximation by expand. Okay, I don't know. There is definitely a way to get the villain model, but yeah, maybe there is a small caveat, but I think it tackles almost all the spin models at once.
Okay.
Yeah.
Yes. The other things that you have like 2 or 3 minutes, so it's
yeah. So my further result is very short. It's just to mention that, you know, these Fourier techniques, they are nice. The way that we came up with them is really because we tried to say something about height functions and not about spin systems, and in the end we managed to get, you know, this very quick result for BKT. But other things is like, well, if you use this exact Fourier duality picture, then for all these type of height functions that have, you know, where e to the minus v is positive definite, so this includes the solid on solid model or something like that, or where alpha is between 0 and 2. You know, all these type of models, they have Gaussian domination on any graph. So it doesn't depend on the graph at all. So they are dominated above by Gaussian interactions. And another thing is that we can do is use it to prove monotonicity and the variance of a height function, at least for the villain model and for XY model. And this was something where you really need to use the non-planar case. So this whole story I said by the duality thing, you really need the non-planar case to be able to say something about planar models. So I think that's very nice. And yeah, I want to leave it at that. Thank you.
So let us first thank Diederik for the nice talk. And then I can ask you whether there's any questions.
I have a very basic question.
Yeah, sure.
Well, actually, 2 questions. The first one is the critical temperature. Well, it's known for the original Ising model, but is it explicit for any other model?
I mean, not for XY, for sure. It's not explicit.
Okay.
This continuous spin model, I don't think there is much hope. I mean, there are some models where it's an explicit computation. I mean, they have to be exactly solvable, and you can maybe compute something. But Ising model, I think, is one of the few models where you know the exact thing. Yeah.
Okay. And the other thing that I'm just curious, for the simulations, you do Markov chain Monte Carlo, right?
Yes.
Even for the spin case.
Yeah, I think it's based. I mean, I must say I use other people's simulation,
Okay.
but it's based on Markov chain Monte Carlo. Yes.
All right. Yeah. Thank you.
So you can do so just to add to this simulation story, because I was playing with them in the. One can do other type of better things at MCMC. So like for Ising model, you don't do MCMC to, especially at low temperature, you do an algorithm called Svensson-Wang, which is, well, there is a Markov chain, but let's put it that it's not a local Markov chain, let's put it that way. And there are ways of generalizing this algorithm to continuous spin systems.
So what is the name? You said
Svensson-Wang. Like, yeah.
Could you type it, please, on the chat?
I think so. So I will make a mistake. So let's please. So there is a paper of Duveda and Falconet where they explain how to do this for, let's say, the VLAN model. So that's the algorithm. So essentially, you pass through the FK representation of Ising. You do something there. Yes.
But it's very specific to that model. I guess.
It works for like a VLAN model, it works for XY model. Because all of them, when you project on one coordinate, you are an Ising model at random temperatures, like in a random environment, let's say it that way. So you project on one time, you project on one thing, you see an Ising model, you do the Ising model story, you come back, you project again in another direction. That's essentially what you're doing. So it is a non-trivial story. So I think I'm going to do the classical question, but it's always something that has made me wonder, is there a coupling story between these dual models? Is there a hope of getting a coupling?
No, I don't think there is. I mean, there maybe, I mean, coupling, I don't think there is a hope of coupling them. It would be super nice if you could find the coupling, but I think there is no real hope of this. You know, what is true is that this computation, it loses even like okay, you can do like exact computation of correlation function and stuff like this, but well, you know, this other representation I have with margin, with the loop soup thing, or with random walk representation, I think it's not a coupling, but it's close to getting information in one model from really both of them, but yeah, getting a coupling, I think it's almost hopeless.
So in a way, what you're doing is like, so the Markov representation helps you for which one model? So for the XY you're using it, or for both you can get the same?
I mean, yeah, I mean the representation. So with you know, my the thing with margin from a year ago, but it's also it's also not good like a coupling, but it's this random walk representation. You know, it's BFS loops in some sense that we are using, but we're using them slightly differently. They're very useful for proving correlation inequalities, but otherwise not so much. But the coupling, I think it's hopeless.
And if I understand correctly, now you can do some inequalities for the endpoint correlation function, 2-point correlation function of this spin system.
So you mean with
respect to beta? So do you know, like, if the temperature is lower, then you have a higher correlation story?
So for the spin models, you could already do it. But for height function, so let's say you take the height function, which would be like integer value. Okay, I mean, here you also knew it already, but just an example or a model where you can do it. And what you're interested in is like the variance squared on a finite graph.
Yes.
And you can show that this thing is always increasing in beta, for example. But for the integer value GFF, you knew it already. But for example, for the height function of the XY model, this was not known. So the fact that this map is increasing in beta was not known for XY model. So
and for the 2-point also, it is also true now for the 2-point function.
Yeah. You can do any gradient thing that you want here. It doesn't matter. Okay. You can get other functions in here as well. I mean, the fact that it's a gradient is just the square here is just reminiscent of the way we do it now, but you could get other things. Yeah.
And also the beta cannot be like uniform, no? Like you can you play with edges, like a beta edges?
Yes. You can do every edge anywhere. Yeah. Okay. So I mean, the proof essentially how it works is, you know, you look at these two models. You have your height function on let's just say a planar graph. But what I want to do is you know, I want to look at. So I have some graph. Let me just make a very small drawing. Okay, I have a small graph, and it goes on. But I want to understand what is how is the 2-point function between x and y behaving as I'm changing, for example, the temperature on this edge, the green edge. So what you can do is you can add the edge between x and y. But in principle, you know, this could break planarity. right? So that's something where you have to do something. But now you map it to the dual model. And there, okay, you have a dual model on a bit of a weird system because, you know, there is no longer a spin system on the dual graph, but there is a spin system. It's just one form with some properties. And what we prove is that that model still has the Genebra inequalities. So we just do the Genebra inequalities proof for this dual model, for the spin model. Okay, but then you can just look at the derivatives of two-point function, and in the end, you know, we add this extra edge. We put e to the minus lambda v of, let's say, xy potential on here. So
then you take it lambda to 0 or something like that.
and then you take lambda to, or the lambda, sorry, the lambda is sitting inside the xy potential, but doesn't matter. Then you take the coupling constant to 0, no, to infinity, so you let it free, and that's it, right? So you kind of remove this edge in the end, and then you get back to your original graph. Yeah.
I see. Thank you. So are there any other questions?
There are some things in the chat, actually.
Yes. No, so it's just Santiago saying bye. So if not, I propose that we thank Diederik again. And now we can stop the recording so we can